After having generalized the law of conservation of momentum and presented the law of conversion of angular momentum for a system of point masses, we will introduce the law of conservation of energy by generalizing the work-energy theorem for a system of point masses. We already saw that the work-energy theorem proved for a point mass states that the change in the kinetic energy E of the point mass is equal to the work W done by the force acting on the point mass. This theorem can also be formulated in a differential form stating that an infinitesimal change in the kinetic energy E of the point mass is equal to the infinitesimal work dW done by the force acting on the point mass. Now we prove the infinitesimal form of the theorem for a system of point masses m1, m2, ellipsis, mn with the instantaneous velocities v1, v2, ellipsis, vn where the forces f bar 1, f bar 2, ellipsis, f bar n are exerted on the point masses in the system. The equations of motion of the system of point masses state that the derivative of the momentum pi of the point mass mi with respect to the time t, or the mass mi times the time derivative of the velocity vi is equal to the net force f bar I acting on the point mass from I equals 1 to n. We can write the infinitesimal displacement vector dsi of the point mass mi as the product of the instantaneous velocity vi of the point mass and the differential of the time t. If we take the scalar product of the equations of motion and the infinitesimal displacement vectors dsi, and add them up, then we obtain the equation stating that the sum of the mass mi, times the dot product of the velocity vi and the differential of the velocity vi from I equals 1 to n, is equal to the sum of the dot product of the force f bar I and the infinitesimal displacement dsi from I equals 1 to n. Since the dot product of the velocity vi and its differential in the left-hand side of the equation is equal to 1 over 2 times the differential of the square of the velocity, we obtain the following expression. The differential of 1 over 2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n is given by the sum of the dot product of the force f bar I and the infinitesimal displacement dsi from I equals 1 to n. In the right-hand side of the equation, the dot product of the force f bar I and the displacement vector dsi gives the infinitesimal work dwi done on the point mass mi by the force along the infinitesimal displacement. We already saw that the forces f bar I acting on a system of point masses include both internal forces acting between the particles of the system and the external forces applied on the system. Then we can split the infinitesimal work done on a given particle into some of the infinitesimal works done by internal and external forces. Considering the expression in the parentheses in the left-hand side of the equation, we define the kinetic energy E of a system of point masses m1, m2, ellipsis, mn with the instantaneous velocities v1, v2, ellipsis, vn, by the sum of the kinetic energies EI of the individual particles in the system, that is 1 over 2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n. Similarly, we can define the total infinitesimal work dW done on the whole system of point masses by the sum of the infinitesimal works dWi done on the individual point masses mi, that is the sum of the infinitesimal works done by the internal and external forces acting on the system. If we substitute these definitions into the original equation, then we can formulate the differential form of the work-energy theorem for a system of point masses, or in general for any mechanical system, stating that a change in the kinetic energy of a mechanical system is equal to the work done by the forces acting on the system. By integrating the differential form of the theorem, we can rewrite it for a finite change in energy produced by a finite amount of work as well. The equations of the energy-work balance show that both internal and external forces appear in the theorem, as opposed to the laws of conservation of momentum and angular momentum where only external forces have a role. The energy of a system of point masses can also be divided into two parts as we will show now. For a given system of point masses, we already define the center of mass or C of the system with respect to a reference point O by the sum of the mass mi times the position vector Ri of the point mass mi relative to the point O from I equals 1 to n over the total mass m of the system. The later is simply given by the sum of the masses mi of the particles in the system from I equals 1 to n. The velocity vc of the center of mass was obtained from the time derivative of the definition of the position vector of the center of mass, and it is equal to the sum of the mass mi times the velocity vi of the point mass mi over the total mass m of the system. Here the velocities are measured in the frame of reference which the reference point O is attached to. Then the position vector Ri of the point mass mi can be written as the vector sum of the position vector Rc of the center of mass, and the vector R'I pointing from the center of mass to the point mass mi, as shown for the point mass m1 in the figure. Similarly, the velocity vi of the point mass is equal to the vector sum of the velocity vc of the center of mass in the inertial frame which the reference point is attached to, and the velocity v' I of the point mass with respect to the frame of reference of the moving center of mass. Now the kinetic energy E of the system of point mass is given by 1/2 times the sum of the mass mi times the square of the velocity vi from I equals 1 to n, can be written as 1/2 times the sum of the mass mi times the square of the vector sum of vc and v'I. By expanding the bracket, we obtain 1/2 times the sum of mi from I equals 1 to n times vc squared, plus 1/2 times the sum of mi times v'I squared from I equals 1 to n, plus the dot product of vc and the sum of mi times v'I from I equals 1 to n. If we look at the expression of the velocity of the center of mass, then we recognize that the sum of mi times v'I is equal to the total mass m of the system times the velocity v'c of the center of mass in the frame of reference of the center of mass, which is of course 0. As a result, the last term vanishes in the right-hand side of the equation, leaving only the first two terms in the expression of the kinetic energy, that is 1/2 times the total mass m of the system times the square of the velocity vc of the center of mass, and 1/2 times the sum of mi times the square of v'I from I equals 1 to n. Then we can conclude that the kinetic energy of a system of point masses is the combination of the kinetic energy of the total mass of the system concentrated at the center of mass, and the kinetic energy of the system determined in the frame of reference of the center of mass. In order to illustrate this statement, we can consider the exploding grenade thrown in the air, which we already used as an example to study the motion of the center of mass of a mechanical system. We saw that the center of mass of the system moves along the same parabola in vacuum as the grenade before its explosion, since the internal forces causing the explosion have no effect on the motion of the center of mass. Then the kinetic energy of the grenade before explosion is given by the first term describing the motion of the center of mass. After the explosion, its kinetic energy will be increased with the second term describing the motion of the fragments, and this increment in energy is caused by internal forces. In the case of a rigid system of point masses, the work done by the internal and external forces acting on the system includes the work done by internal and external constraint forces. However, the work done by constraint forces vanishes in many cases, as we have already seen. In fact, it can be shown that the work done by constraint forces vanishes if the constraints imposed on the system are independent of time. For example, such a time-independent constraint is the several time aforementioned condition of the fixed distance between two arbitrary points of a rigid body, which states that the sum of the square of the differences between the corresponding Cartesian coordinates is constant during the motion of the body. Now we apply the work-energy theorem for conservative systems, which we will introduce below. If a system of point masses is a free system or the constraints imposed on the system are independent of time, then the work producing the change in the kinetic energy of the system in the work-energy theorem is the work done by all the free forces acting on the system. This work generally depends on the path along which it is done, where this path is represented by the individual trajectories of the particles in the system between their initial and final positions. Nevertheless, in many cases the free forces acting on the system are such that the work done by them does not depend on the path along which it is done. Furthermore, the mathematical expressions of these forces do not have an explicit dependence on time. We already considered such forces called conservative forces when we studied the law of conservation of mechanical energy for a point mass, stating that the sum of the kinetic energy and the potential energy, that is the mechanical energy of a point mass, is constant under the influence of a conservative force. As a result, we also saw that the work done on a point mass by a conservative force is equal to the decrease in the potential energy of the point mass. We call a mechanical system a conservative system if the free forces acting on the system are conservative forces. The case of conservative forces acting on point masses can be generalized to conservative mechanical systems. If in the initial state A of a system of point masses the particles have the positions R sub A1, R sub A2, ellipsis, R sub AN, and in the final state B the point masses have the positions R sub B1, R sub B2, ellipsis, R sub Bn, then the potential energy E of the system in the states A and B depends on these initial and final positions. Because the potential energy depends on the positions of particles in the system, each point mass has its own contribution to the potential energy of the whole system. The internal part of the potential energy is given by the interaction potentials between the particles in the system, assuming that the interactions are conveyed by conservative forces, whereas the external part is determined by the potential energy of each point mass in the presence of an external conservative field. If the conservative system evolves from the initial state A to the final state B, then the work W done by all the free forces is equal to the decrease in the potential energy E of the system depending only the states A and B. For differential displacements in the positions of the point masses, the infinitesimal amount of work dW done by all the free forces is equal to minus the differential of the potential energy E of the system. Now we are ready to formulate the law of conservation of energy for conservative mechanical systems. When we considered the evolution of such a system from its initial state A to its final state B, we were able to express the work W done along any path between the initial and final states as minus the difference between the potential energies in the states B and A. By applying the work energy theorem, that is expressing the work W as the difference between the kinetic energies in the states B and A, we obtain the equation stating that the sum of the kinetic energy and the potential energy in the state A is equal to the sum of the kinetic energy and the potential energy in the state B. That is, the mechanical energy of the conservative system in its initial state is equal to the mechanical energy of the system in its final state. This is the law of conservation of mechanical energy for mechanical systems, telling us that in a conservative system the sum of the kinetic energy and the potential energy, that is the mechanical energy of the system, is constant if any constraint imposed on the system is independent of time. Due to the decomposition of the total work into the sum of the work done by internal forces and the work done by external forces, the potential energy of a conservative system is the combination of the internal and external potential energies. It is possible for a non-conservative system that its internal forces are conservative ones but the external forces acting on it are not. In this case we can talk about the internal potential energy of the system, but no external potential energy exists for such a system. The balance equation stating that the differential of the kinetic energy is equal to the infinitesimal amount of work done on the system given by the sum of the infinitesimal works done the internal and external forces still holds. But only the infinitesimal amount work done by the internal forces can be expressed as the negative differential of the internal potential energy of the system. As a result, the balance equation tells us that the sum of the differential of the kinetic energy and the differential of the internal potential energy of the system is equal to the infinitesimal amount of work done on the system by the external forces. Instead of the differential form of this equation, we can also use it with finite changes, stating that the sum of the change in the kinetic energy and the change in the internal potential energy of the system is equal to the work done on the system by external forces.